Hey everybody, Dr. G here with the Week 3 Lab Supplement. I'm trying to get back into content development and sharing mode. The first couple videos were all from last year, so I'm trying to start building some new stuff and give you some multi-modes and ways to think about things in different ways. So today I'm giving you a supplement video for this week's lab, which will be on campus, checking out our amazing campus and some really cool and fundamental ideas across that walk. We talk about watersheds, treads and risers as a concept, and alluvial soils. And this will provide us context for both anything we talk about on campus plus our further farm exploration, because we're talking about these concepts again and again and again. So I haven't been doing this in my other videos, but let's just take a moment to become centered and focused on what we're doing. Enjoy this moment. Oh, wait, yep. I do that moment of Zen in all my live Zoom classes, and I want to try to bring it back into the videos. It's just a moment to honor being present and being prepared for what's coming next. So here's what we're going to talk about in this video or this week. Take a deep breath as we just did. We're going to talk just briefly about watersheds and the concept of alluvial environments, the tread and riser geomorphic or terrace and riser geomorphic approach, alluvial soils and what we have locally around Chico and the alluvial fans that we have here on Chico, and then a quick concept about monoliths and some examples of monoliths. So our country with legal boundaries, right? The US of A here, we got Alaska and Hawaii down at the bottom, and then the lower 48, here we are over in California. What's funny about this, when you really think about it, is that all the lines are straight, and where lines aren't straight, it's likely where there's a break, a natural boundary between two places based on a river or a watershed. Most of these lines represent legal boundaries that are based on latitude and longitude, and in some cases they do kind of can coincide with areas that make sense why one state has a certain area and not. If you look at the boundaries around California, the northern boundary of California is really where the redwoods stop in the north. There's not a lot of redwoods in Oregon, and that's pretty much where they end, and some other things. But they're arbitrary, they're legal. So if we looked at California and the U.S. based on watersheds, right, places that accumulate and drain and convey water, you'd have a much different setting, right? You start thinking about the Klamath River Basin, the Willamette, the Columbia River Basin that runs from all the way up here into Canada and comes out of Portland, the Salish Basin, which is getting into the Puget Sound. Here in California, we would have the Sacramento-San Joaquin River Basin, these Southern California basins, and so on. What is a watershed? A watershed is a physiographic boundary where water flows into a catchment that flows out to the next catchment or the next watershed, or ultimately to the ocean or a lake if it's inland, right? Watershed concept we're going to talk about this week in lab. For Butte County, here's our watersheds, right? Here's Chico, and we could talk about the big Chico Creek watershed right here that flows down into Chico and flows through our campus. Maybe not so much right now this year because campus is pretty dry, but we have some other watersheds here. We have the Pine Creek watershed and Rock Creek. We have the Butte Creek watershed here that flows out just south of town. And then we get into the Feather River watershed to the south, which is quite large and expansive. That is one of the most hydrologically productive watersheds in California, outside of the Klamath, because the Klamath is massive and drains multiple large rivers into it. But we'll be talking about watersheds, right? And what happens in a watershed? You have alluvium, you have erosion in certain parts, deposition in others, and soils across a watershed vary depending on a variety of different factors. So one thing we're going to see this week in lab directly is this concept of a tread and riser geomorphic sequence. Check out the term geomorphology. You can decompose it yourself, geo meaning earth and morphology meaning shape or form. And the tread and riser is a great way to start thinking about the bottom end of a watershed or the floodplain or the alluvial delta, right? Places where material and water from the upper watershed are carried down and where the energy in the system becomes limited, the gradient, right? The difference of elevation that allows for things to flow downhill, and you get to the bottom and you create these tread and riser type situations. I bring this up because once you see this, you can't unsee it. Every watershed you've ever been in, every creek and stream down at the bottom in the valley, you'll have seen these types of features, and we're going to see them on campus on Wednesday and Thursday. On the left here, you can see a schematic diagram of the actual channel, bank full channel, surface 1 right in there. That's the tread. This upward slope going out of the watershed or out of the creek to this next tread. So tread, riser, tread, riser, tread. Places where there's old surfaces, terraces, or treads were once the watershed or the floodplain, pardon me. And as sea level change and mountains build, and as the dynamics of the watershed change, incision and downcutting happens. And these more complicated geomorphic situations happen with multiple surfaces and scarps or treads and risers. We will see this in the Alumni Grove, the Alumni Glen, or the Machupta Village site on campus, and we'll see it downstream again where there's remnants of this feature. Once again, you will start to see this everywhere. It happens in the current environment that we'll see on campus, and it's been used as a historical reenactment tool to understand much farther back in time. Here's an example of a much older terrace sequence from the Mojave Desert with current alluvium, active floodplains and channels, and this series of treads and risers. They can go back into 450 or greater 100,000s of years ago, depending on the climate at that time. We haven't talked about climate and moving back in the climatic period, but just know that these are really great things to think about, and you can start to appreciate what an environment used to look like. These are also really good tools to think about soil development, and we'll leave that there for later. So now I just want to focus down in on the alluvial fans of the Southern Cascade. Once again, you can see over here on the right, here's Chico, here's Bidwell Park and the campus right here. That little green strip is our campus. And all of this land from up here on Deer Creek through these smaller drainages and to Big Chico Creek and down here to Butte Creek, all of this green checkerboarded agricultural area are the alluvial fans where watersheds and floodplains dump out sediment and water in the low slope areas down in the bottom, in the valleys and bottomlands. So once again, we talked about Big Chico Creek. Here's a little bit better delineation of the Big Chico Creek watershed coming out of the headwaters up here around 6,000 feet on Colby Mountain, making its way down through the canyon and coming out through Big Chico Creek. Right in here is about where Bear Hole is, and onto our campus and out towards the Sac River. This red delineation here is pretty straight, and that's because right next to Big Chico Creek is Butte Creek, and it's a much larger and a much more productive not much, but it's a larger and more productive watershed than Big Chico Creek, and you can see how its influence and the interaction of these two alluvial fans created this straight line where the water from this one was heading out and the water from this one was heading out, and they were co-interacting in that location. But here, we've talked about this a little bit. We're going to be on campus today. Down here, you can see the head of the university farm, which is ultimately on Butte Creek's watershed, and I mentioned that in my section on Wednesday. But we're going to be talking about these alluvial soils again and again because they're generally our most productive, youngest agricultural soils that we manage actively and intensively for crop production. Some examples of our local soils. We haven't gone here yet, but in 2 weeks we're going to get in the pit. We're going to see these pits at the farm. This pit here on the right is an example of pit we're going to see at the university farm. Here's the soils as mapped that you would find across those alluvial fans that we just talked about. The almendra, which means almond in Spanish, Conejo, Vina, Charger, and Chico. Those are all these mollisols or RG and haploxerols, and we'll talk about that when we get into taxonomy. They cover about 150,000 acres around Butte and southern Tehama counties. And they're all these nice, deep alluvial soils that formed over fairly recent time frames, right? We're talking about 20, 30,000 years back in time, which really isn't that long when you consider the age of the earth and things like that. So quickly want to change gears and show you a little bit of your future, right? So here's an idea, this concept of a monolith. It's a noun, a large single upright block of historically stone, but in this case we're going to talk about soil, right? Being able to collect upright blocks of soil, especially one shaped into or serving as a pillar or monument. So here on the right is an example of our university farm soil that was collected in that vein. Top of the soil here down to about 1 meter of depth at the bottom, and this is a monument to the soils that we have. And I'm going to tell you quickly about these because we're going to be looking at these monuments or these monoliths across soils collected in the area throughout the rest of the semester. So you might ask, how would you create one of these? How would you collect a monolith? Well, monoliths are freaking rad, right? It's always fun. You always got a big pit. In this case, we took this soil and we're able to dig it out into the right shape using a metal frame, and I'll show you these in class, and then being able to take out an intact section of soil from that pit face. We've done it in my Plant Science 451 Soil Genesis class. We've collected them. Here, these were collected during the summer with some other students, and it's just always fun, right? It's always fun. It's a challenge, and you get to see these big blocks of soil come out. Now, what happens? You have to process them up and prepare them so you can enjoy them. So here, just the idea of collecting that sample and getting it ready, picking off the face and getting it to a position where you can set it in resin or glue and be able to enjoy it and check out its features, right? Check out what it looks like. Not just some bag of something that you collected, but some of those features that are only seen when they're in their natural setting, right? This is one of those interfaces of soil and artistic flair, right? We're talking about how not only is soil something that we fertilize, irrigate, manage, but it's something that can be brought out of the pit and able to share with other people and get them to appreciate the features, the function, the depth, some of the things that soils provide, which are often difficult to see because they're underground. So we're going to be looking at these monoliths throughout the rest of the semester. This is a transect from the university farm, these pits, these first three, to west of campus and to north of campus up by Vina at the New Clairvaux Vineyard. And you'll be able to see in these monoliths soil formation, soil structure, some of the influences of agricultural management on soils and some of the features that they form. And it'll be a great way for us to think about what is Chico sitting on? What's the power? What is some of the benefit that the soils in Chico have? And why has Chico been such a successful place for agriculture and just a great place to be? So hopefully this approach was interesting. Like I said, I'm going to try to start building these kind of pre-lab videos to give you some information that might not be as easily shown in class. But just in review, we talked about the watershed concept, alluvial soils, deposition. We talked about the tread and riser concept of downcutting and the geomorphic development of a landscape, which we're going to see in lab. And then we talked about monoliths. And how do we get people to appreciate soils, not just something that you drive on or grow crops in, but for other features, right? And remember, that's one of our goals in class is for you to connect soils to your life, connect soils to things that aren't just growing crops and that type of thing. Okay, so till next time, take it easy. I hope you're learning a lot. And remember, the goal is for you just to learn, not to be stressed out. All right, take care of yourselves, wear your mask, get vaccinated, and we'll get through this somehow. Later.